We went from about 23% to 54%. Now think what's going to happen to the runoff. All that water is going to be surface runoff. We love paving everything, right? Classic example. So this is not only the case in the urban environment, but it's also the case in the agricultural environment. And I'll show you an example here of the Sumas watershed, which is half in the United States and half in Canada. And it comes from the US into Canada. And they pollute us in terms because there's a landslide up here which has exposed a geological formation which is full of asbestos. And every time there's a flood, all the sediment gets down and gets deposited on agricultural land. And next door is an aquifer, the Abbotsford Aquifer, and the water flows south. And we have completely contaminated the aquifer with nitrate, so we're compensating. They're polluting us and we're polluting them. So this is the most intensive agricultural watershed used in Canada in terms of animal stocking density according to Statistics Canada. We have dairy and chicken, and we produce about 17 million chickens every 6 weeks. So we did a nutrient balance in this watershed, and we calculated how much surplus nitrogen is being applied to the land above what the crop needs. And so everything here in yellow means anywhere between 0 and 100 kilograms per hectare of surplus. Anything in orange is 200 to 300, and the one in red is above 300. That is, the high one is almost double what a crop would actually need, and that's the surplus of it. So, here comes the stuff, which is really critical. Temperatures in this watershed are increasing, but precipitation over the historic time has not changed at all, right? So what is happening to the river? So the temperature has not changed, but the river is actually generating more precipitation. How do you explain this? We not get more precipitation, but all of a sudden the river starts producing more water. In fact, if you look at this, in the first 10 years, it produced about 36% surface water, and now it produces about 49%. So this is about a 13% increase in discharge in the river. And if you look at the 20-year difference, it's about 10%. So the river has now increased discharge by 10%, and now you have to start thinking, why would that happen when you have no more precipitation? Soil compaction. If you compact your soil, you're going to have more surface runoff in agriculture. And remember, we tend to aerate the soil, so as soon as you plow your soil, you get rid of your carbon. In fact, if you look at your prairies, the Chernozemic soils in the prairies, at the time first the farmers came in, it was all on the grassland, and the organic matter content was somewhere between 12 and 14%. And over 100 years, we're now down to about 6%. That means we have lost 2/3 of the carbon pool, and this affects the infiltration, water holding capacity, nutrient holding capacity, and the CO2 storage. So can I prove that compaction is actually happening? Well, we can show that the surface runoff has increased. The evaporation also has increased because it's getting warmer, right? So their only explanation would be, have they generated more drainage tiles or soil compaction with surface runoff? And if you then look at this, what I'm showing you here is the number of animals per hectare over time. And if you look at the bottom, it's the number of animals per farm. And we're now at an exponential rate, which means we have more animals, we're going to have more compaction. Or, if you look at the Canadian side, the same thing. And then we do these kind of things. Turf farming, which is compacting everything and losing the soil every year because you harvest 3-4 times and you move it. or different practices. So even in agriculture, we're doing the same thing as we do in the urban environment by creating more surface runoff. And this is the wonderful thing when you're an academic. You have access to the brightest of society. And so what you can do is you put them into the same watershed every 5 years, and you find out how things are changing. So you look at this watershed, and you look at nitrate values in the 70s, in the 80s, in the 90s, and now, and you can see all of it is increasing because of agriculture intensification. And if you compact your soil, more of the stuff you apply is going to run off into rivers. And just the green line is a forested water control site in the same watershed, and see that hasn't changed over historic time. And if you do that, you're going to have more flooding. And so we're going to have all kinds of issues now with this asbestos problem, because every time we get a flood, we get more asbestos sediment deposited on agricultural land, and you know it's very carcinogenic, it's mesothelioma, and then nobody wants to deal with it, and this is going to be a huge challenge for us. Okay, so I'm not going to talk very much about urban stormwater management because I know my colleagues there will dazzle you far better than I can, but I want to just give you a little bit of an idea of what we actually can do. Typically what we have done is we told the engineers to drain. And what I'm now saying is, you as an individual landowner has a responsibility to help stormwater management. Because remember, when we move into the city, you expect the city to take care of everything, right? Yeah, your drinking water, your wastewater, your garbage, everything is taken care of. And now we're saying, given this climate variability, we need to start managing water and rainfall at the property site. And then the municipality comes in, because that's then the neighborhood, because then you have to deal with roads and parking lots and all that. And then we need the province, because then we need to start looking at the watershed, because municipalities usually have no jurisdiction over the watershed. So they need to work together. And each one can do something. And rather than doing the traditional approach, we're talking about innovation. How do we retain the rain on the site? How do we store and delay the runoff? And what do we do at the watershed scale? And so just a few examples. These are all the things you can do as a house owner. You can have a green roof. This is probably not practical in some cases, but certainly the industry could do that. The equipment mounted co-op, which you probably know, is very, very popular. They're very green. They built 2 new buildings, and they're completely green. They have a green roof. They collect the rainwater, and they use it to flush toilets. Minimizing your impervious surfaces, roof water harvesting, 30 centimeters of topsoil before you even put your lawn in. You could even ignore your lawn and make a xeriscape. Cover your urban, introduce your urban trees. And I was a total fool, because when I went to Calgary some years ago, I told them, well, that's probably not a good idea in Calgary because of your climate. And then Bird corrected me and he said, you're all wrong. Because if you put in swales, the swales always carry a little bit of water, and that's sufficient that you don't need to irrigate. So again, don't believe what all the academics tell you. So, and then at the municipal level, we need to change the road system with no curbs, no gutter, infiltration systems, swales, detention ponds, wetlands. We're building wetlands in the city all over the place. And of course, everybody screams and yells and said, we don't want mosquitoes in our neighborhood or West Nile or whatever. And we have now enough evidence now that we can minimize that impact by all kinds of wonderful things. And Michael Jackson, not the singer, has a company, and it's a mosquito company. And he actually has contracts for the city to minimize mosquito impacts on wetlands in the city. And the way he does it, he simply says, make sure that the inflow and outflow of wetlands always moves a little bit. So he puts in a solar panel or windmill to make sure it moves. Secondly, make sure it's not eutrophic. If you have all the blue-green algae, harvest it. And then if you remove it, that helps. If you plant your plants, the wetland plants, make sure there's enough spacing between the plants so that the UV light can go through. Put in stickleback, which are fish which can survive some really contaminated conditions and eat the larvae. And then you go in at the larvae time and you can do that. And then at the watershed scale, we need to really re-engineer the buffer zones. We need to go back to nature and don't channelize your river and make sure you have a very good buffer zone so you can actually put your wetlands into the buffer zone and hold the sediment back and the nutrient back. And we need to deal with stormwater in a totally different way, and I'll show you an example. So channelizing your river on the left restricts all the kind of natural things which nature does. And so if you go and do no longer channelize your river, the river can act, the water can actually go sideways and restore your groundwater and do all kinds of wonderful things. So what do we do with flooding now? What did they do in Calgary? Build more structure, build more dams and dikes and concrete stuff. We need to rethink this, because if we get these big storms, that is no longer sufficient and it's too expensive anyway. What we should be doing is designated areas where you temporarily store water during big events. Here's an example from the Mississippi. They had this big storm coming. They decided if they don't do something, 7,000 houses will be flooded out. And so they breached the dike here, stored the water in this whole area of agriculture, and released it 2 weeks later. And that saved them flooding 7,000 houses. And I know on the Red Deer, on the South Saskatchewan, they had some flooding about 3 years ago, and they were going to flood deliberately some 500 houses. And how would you like it if the government comes and said, look, sorry, we have to breach the dike because otherwise the whole city will be underwater, and you wouldn't be very happy. So what they did 24 hours before they did this, they went out with GPS trying to figure out where the water is going to go. Why don't we look at every topographic condition in your watershed where you could actually temporarily store that water and release it later? And in this case, the farmers were back in business within 4 to 5 months. And if we compensate them, that is cheaper than building structures. So that's an idea which I'm promoting quite heavily, but I get lots of resistance, of course. So let me show you a good example of domestic water use in small mountain communities. This might be of interest to some of your rural communities. I sent a student around the Columbia Basin in 2005, and she talked to all of the engineers and said, I was curious to see how much water are these small communities using. And she came back after the summer and she came up with astronomical numbers. 1,500 liters per person per day in some communities. Vancouver is bad with 330 liters per person per day. 1,500. And well, we figured that can't be right. Remember, none of these communities were metered. So all they did is they went to the engineer, and the engineer said, well, we're releasing so much water from the reservoir and so many people, and that's it. So the Columbia Basin Trust said, well, why don't we start a conservation program? And they put up some money and said, if you're interested in reducing your consumption by 20% over a 7-year period, we'll finance that idea. So in 2009, 20 communities signed up over a 7-year period to reduce their water consumption by conservation. So this provided us with a fantastic opportunity because 14 communities did it in a consistent manner, so we can actually compare the results. Here are all the communities. They're right next door to you. Now, you think water conservation is easy, right? I'm telling you, well, all you need is change behavior. Bad. Look at all the factors which are important in terms of water conservation. The first one is, of course, climate. If it gets hot, in the summer, you're going to use more water, particularly if you have gardens and stuff like that. If you get a lot of precipitation, that will reduce your water consumption. So climate is critical. Secondly, depending on how much outdoor activities you do, obviously that makes a huge difference. Just to give you an idea, the Okanagan Basin is the driest watershed in Canada, and 48% of their drinking water is used for lawns. That's not a pretty good idea, and if you want to do conservation, that would be a way to start reducing it. The next thing is, of course, beliefs. If you ask the people in the Columbia Basin whether they have a worry about water, they will tell you, are you kidding? We got plenty of water, plenty of snow, we don't have to worry about it. How do you then change that mentality? What kind of incentives you put in there? What kind of regulations are you going to put in there? And then, of course, the management of your system is critical, and I'll show you later on why this is critical, because Cranbrook loses 50% of their drinking water by leaky pipes, because they have very old infrastructure, these very old mining towns and so on. They have no asset inventory. They always fix pipes when they leak, right? And then, of course, the infrastructure, the longevity is the critical thing. So these are the kind of challenges we face when we go to water conservation. So how do we actually measure how much water is used for residential purposes? You have to look at this in this way. ICI, institutional, commercial, and industrial water. Every community has a component of that. And then we have this non-revenue water. That's firefighting and stuff like that, which doesn't pay, but it has to be used. Then you have the leakages, and then you have the residential water. So if you're not metered, how do you determine that proportion? So community A is like this, and community B is like this. So each community has different proportion. So over these 7-year periods, as I mentioned to you, we had 2 of the wettest years and 1 of the hottest years ever in 100 years. So remember, if you try to have conservation and you start and you do well, and then all of a sudden you have a drought, you need other measures in place, otherwise you're not going to show any improvement. So the way we can actually show this is by looking at the temperature. Here's the temperature, and here's the total water use. And all the blue dots are the 6 years from 2009 to 2014, and the red is the 2015, which was the big drought. So this community here, you can see pretty much no problem. And then the drought came, and they were actually quite successful in reducing their water consumption even during a drought. And what's even more important is when we look at the winter time, when it's cold, people use the same amount of water. But then once the summer comes, the curve goes up quite steep, right? So this community was very successful because they went to universal metering. Similarly, this one here. And then we go to this one, and you see this one wasn't very successful at all. And then what has happened here? How do you explain this one? 6 years, and then 5 years, sorry, and then for 2 years they were down here. They had a major leak in their distribution system, and they fixed it. And by doing that, they not only reduced their water consumption in the winter, but also in the summer. Now you can do something interesting. How do you explain this community? They use more water in the winter than in the summer. They bleed the pipes. That's in the high mountain areas in Elkford, high elevation. They're worried about freezing pipes. They let them bleed year round. And so you get a totally different pattern. So you can see each community has different issues and different problems, and you need to start thinking about how to address this. So what we can actually do is this. You can see, so the summer, each community, these are 3 different communities. You can see the steepness of the rate differs between communities. So these guys, with temperature increases, their consumption goes up much more dramatically than this one. And we now figured out that at about 14 degrees in the Columbia Basin, this is when people start using more water. So we could actually do a regression line and calculate how much more water are they using for every 1 degree increase in temperature. And if we do that, you can see that Nelson uses about 19 more liters for every degree temperature versus Trail, which uses 80 liters per person, which is fascinating because that gives you an idea where should you actually start focusing on reducing your consumption. You could then look at this in terms of every month. All the red at the blue is where they decreased their consumption, and the yellow is where they didn't. And so, for example, Elkford wasn't successful at all. Neither was Nokost, but they were not successful in the winter, but were pretty successful in the summer. So each community has differences, and the ones in blue there, they were successful continuously. So we can then show you how successful were they as opposed to the beginning of 2009. So the blue bar is 2011, 12, 13, 14, and the red is 15. So this community did a very good job initially, but missed the drought and weren't very successful during the drought because they didn't anticipate it. And then you look at this one and this one, they were consistently able to actually reduce their consumption over the whole time period because both of them went to metering. And then you look at this one, this is Caslow, and they fixed the big leak. So then they had a massive reduction. And then you look at this one, and they were not successful at all. So now comes the big problem. How do you then, if they're not metered, 12 of them were not metered, how do you then determine how much is actually used for residential purposes? So the best we could do, knowing the leakages from the engineers, we could say Ericsson is somewhere between 30 and 40% of all the water they use is for drinking water. And other ones like Fruit Whale is between 60 and 70% of the total water uses for domestic purposes. And so Environment Canada did a survey of all the municipalities in Canada in 2011 and published it in 2014, and they came up with some interesting numbers. Here are very small communities, medium-sized communities, and large communities. And this is how much they claim is used for residential purposes, for ICI, institutional, commercial, and the others, in industrial use. And here's the leakage. And the leakage is anywhere between 9 and 12%. So we could actually then go and say, this is what Environment Canada showed us, this is what we showed, and then we can apply the ICI from the survey to the Columbia Basin, and then we can come up with an estimate of leakages. And our estimates now are somewhere between 26 and 43%, which is huge. And remember, these communities don't have resources, they've been completely neglected, they have old infrastructure. How do we start developing a good inventory? And so we can then determine how much water each community is using. So the blue is the total water use per community, and the black is the residential water use per community. And if you do that, you can see the range. And what is interesting, in the Columbia Basin, this is the range. If you look at the Stats Canada, this is the range. So we're still way above the average of the Canadian average by provinces. So now comes the question of finance. How do you actually pay for your water? Do you have any idea how much you pay for your water? Average It's about $1. $1 for 1,000 liters. How many of you buy bottled water? You don't want to admit it, right? How many of you buy bottled water? 250 milliliters? Quarter of a liter? How much? $2.50? We pay $1 per 1,000 liters for drinking water, which is safe and pure, and then people don't use it because they think it's not safe. Crazy, right? So if you're not metered, then you're going to have a flat rate. Let me tell you an embarrassing story. Vancouver is not metered. I pay $550 a year and I can use as much water as I want. Totally ridiculous. If you're metered, you can charge people by volumetric use. And you can have block rates because people always say, well, you can't charge people on a volumetric basis because that's not fair for the poor people. Well, if you have block rates, you can make the first 20 liters or the first 50 liters cheap, and then as you go up, more expensive. South Africa has a law that the first 25 liters per person per day is free. And then as you go up, you use more. So here's the challenge when you're not metered. So let's see what's happening here. These are the flat rates which these communities charge. So it ranges anywhere from about 200 to 560 liters. Total difference for each of one of these communities. And then if you look at ICI charges, you're in for some really interesting stuff. Schools and hotels, they charge hotels according to the number of rooms. And look at the range between the communities. They charge schools by the number of classrooms. And again, here's the difference. They start churches for water. So every community has a different way of financing the same. All depends on your economic condition. And then we can actually use our data for residential and then convert it into how much that water costs. And if you do that, this is the range we came up with. So anywhere between 44 cents per cubic meter to $3.03. And how does that compare to the rest of the world? You look at the US and Japan, they charge about $1 per cubic meter. Canada is a little bit above $1. Look at the European countries, anywhere between $2 and $7 per cubic meter. Then you have actually enough money to start thinking about your infrastructure. So Environment Canada showed this. These are the small communities. This is how much water they use on average in Canada when they're metered, and this is how much they use when they're not metered, and you see the difference is anywhere between 18 and 50%. So metering is about the best thing you can do. And my argument is, you love your smartphone, don't you? You have accepted that technology without consideration. But we have smart meters. And the smart meters are so sophisticated that you can actually track any individual on a minute-to-minute basis. Why don't we go to the 21st century and use smart meters? It just blows my mind. Everybody says it's too expensive. Yeah, it's expensive initially. But let me show you an example. So Vancouver isn't metered. And now what they're doing, they're saying, well, every new house has to have a meter. Well, how long do you think it's going to take before everybody has a new house? Probably 20, 30 years, right? So if you install now a smart meter, 20 years from now, that meter is totally obsolete. How often do you change your cell phone?
3 years.
Mm-hmm. So then we need to do it again. So why not bite the bullet, buy the bloody thing now, pay for it? The Royal Bank has this Blue Water Initiative, and they do a survey of Canadian opinions every February. And they came up and said the public is 70% willing to pay more for water because it's important, that politicians don't want to address it. So what was accomplished? All these were the challenges which we had. Obviously, if you can't account for water, how can you actually do anything? we meter everything else, and it's totally acceptable for your gasoline, for your gas, for your electricity. Why not water? You probably are more progressive because you're all metered, right?
We are.
System management and calibration is a real problem. When do you actually do leakage testing? Do you know in the Columbia Basin you have to do this either in November or February, and you have to do it between 1 a.m. and 4 a.m. This is at the time when nobody uses the water, so you put in meters in different systems, and then you know what is actually leaking. Well, that's pretty tough. In the winter time up in Caslow, not a particularly easy thing to do. So we need to start doing this in a much more comprehensive manner. So universal metering, water loss management, asset inventory, equitable water pricing, source water inventory and source water protection, education program, and food security is becoming an issue. These mountain communities now have said, we want to grow more local food. Well, guess where they get their water from? From domestic purposes. That's a new kind of thing we need to deal with. So we accomplished quite a bit in this, and for me this was a fascinating thing because you never get the opportunity to look at a whole range of different communities and see how they are coping with these new initiatives. And remember, one proposal doesn't work. You have to look at all the different circumstances for each of the communities. So, conservation options, the basic conservation for all seasons is really metering everything, charge a proper rate so we can actually improve the infrastructure, use low flush toilet systems, and I argue with this all the time. I used to have 20 years ago a conventional system, 21 liters per flush, and I go 7 times a day. And if you get older, you go more, right? And now you have the 3 and 6 liter systems. If you switch from that, you can save 150 liters per person per day. That is half of what we use. Very simple, right? And then, of course, in the winter, you need to do all of this stuff about insulating pipes, leakage detection and all that. And in the summer, you got all these kind of things to do, which is really important because we should really start focusing on roof water harvesting, reducing our summer footprint. I have a rain barrel and I have a big vegetable garden and I never use domestic water, and I got through to 2015. Just about. So we not only need to look at the urban situation, but we also need to look at forestry, agriculture, and urban in a watershed context. And here are all the opportunities you have to actually look at the integration of these things. And this is where we're struggling, because even at the university we have programs in forestry, in agriculture, and engineering, and we never talk to each other. And so what you're doing here is the only way to start looking at the new challenges which we face with climate change, greater variability. Thank you very much.